Okay, so for the rest of the vectors topic, we're looking at intersections and angles. So we're looking at every possible intersection. Intersections of lines with lines, lines with planes, planes with planes, planes with planes with planes. But in each case, your intersections, where you're actually looking for the point or line of intersection, it's always going to be some form of simultaneous equation thing that you want to do, which may or may not involve Gaussian elimination, depending on how complicated it is. The angles, you're always going to use that trick from higher where you use the scalar product to find the angle between two vectors. So you use the definition of the scalar product, the dot product. But remember, you can work out the dot product from the components as well, a1, b1 plus a2, b2 plus a3, b3. So if you work out the dot product with these two ways, you've got the magnitude of the two vectors, and you've worked out the dot product using the components, then you can get the cos of the angle between them. So today we're looking at two lines, and we're looking at how to show if they intersect. We're looking at finding the intersection point, and we're looking at finding the acute angle between them. So, two lines, will they always intersect? Well, in 2 dimensions, they're either going to intersect or they're parallel. Now, in 3 dimensions, they can also be parallel, in which case they're not going to intersect unless they're actually the same line. But in 3 dimensions, you also have another possibility. If you think about a cube, an cuboid, and you think about this line here, which can carry on into space, and you think about this line here, and carry on up and down, they are never actually going to intersect, no matter how far you carry them on. So straight lines do not have to be parallel to avoid intersecting. In 3 dimensions, they can be what's known as skew. So they're not parallel, but they will never intersect. At any rate, we can show mathematically whether they intersect or not, which is much better. So here we have 2 straight lines, and these ones do intersect, so we're going to show that they do intersect, we're going to find the intersection point, and we're going to find the acute angle between them. So first of all, you always want to put them into the parametric form. So we're going to say, so this is the form, symmetric form, we're going to say that equals lambda, because if we do that, we can then rearrange all of them, because we've got x over minus 2 equals lambda, which is the same as saying that x equals minus 2 lambda. And we can rearrange this one to say that y equals minus lambda minus 2. And we can rearrange this one to say that z equals 2 lambda plus 9. Okay, and if these lines are going to intersect, then there must be a point for line 1 and line 2 where the x, y and z coordinates are the same for both of them. So there must be a point where minus 2 lambda equals 8 minus 2t. Where minus lambda minus 2 equals minus 4 plus 2t, and so on. So we just set up those equivalences. But we've got 2 unknowns, we've got lambda and we've got t. So we only need 2 coordinates to determine what lambda and t would have to be. And then we can use the 3rd coordinate to check whether that agrees in the 3rd dimension. And that tells us whether the intersection point actually exists or not. So let's set up the first 2. We've got x coordinates here, so we can combine them, but with that to give us that 8 minus 2t must equal minus 2 lambda, and then we can combine this with this, oops, poor thing, which would give us that minus 4 plus 2t equals minus lambda minus 2. And if we add those two together, then we're going to get rid of the t's. So let's do that. So put plus in there, we're adding all of that, and we're seeing what we get. So those cancel. 8 plus negative 4 gives you 4 equals minus 2 lambda plus another minus lambda gives you minus 3 lambda. And we've got a minus 2 there. And if we rearrange that, we get minus 3 lambda equals 6, or lambda equals minus 2. So that's just simultaneous equations. So 8 minus 2t equals minus 2 lambda. So we can put that value in. 8 minus 2t equals minus 2 times minus 2 equals 4. So if 8 minus 2t equals minus 4, then minus 2t equals minus 2t equals minus 4, so t equals 2. Okay, and so we've worked out lambda and t. So we've got lambda equals minus 2, and we've got t equals 2. Now, if these lines actually intersect, then this value of lambda and this value of t should give us the same z coordinates as well. So let's have a look. For line 1, we had z equals 3 plus t, which would in this case be 3 plus 2 equals 5. For line 2, we've got z equals 2 lambda plus 9 equals 2 times minus 2 plus 9, which equals 5. So the z coordinates are the same. So we can say that this is consistent, and therefore the lines do intersect. So this is basically because you are starting off here, you've got 3 equations and only 2 unknowns. So you can use the first 2 equations to find the 2 unknowns, and then you can show whether the system is consistent by using the third equation. It's come out as consistent, so the lines do intersect. So we've worked out the z coordinate here. We can work out the x coordinate and the y coordinate using either of these 2 systems. So x equals 8 minus 2t, and then you can substitute in equals 8 minus 2 times 2 equals 4, work out the y value, and then that gives you the coordinates of the point where they intersect. Right, we also need to be able to find the angle of intersection. Okay, this question was actually an exam question, and what the question said was show that the acute angle between the lines is cos to the minus 1 of 4/9. So if you go back to your original version of line 1, looked like this. So you can turn this into the vector equation of a line. So for the x coordinate it's 8 minus t, or 8 plus t times minus 2. So we can convert that into a vector form. So L1 becomes 8 plus t times minus 2. And you can see the y and z coordinates can come out into that as well. And that is the direction vector of line 1. And line 2 we can do the same thing on. It becomes 0 minus 2, 9 plus lambda times minus 2 minus 1, 2. And that gives us d2, the direction vector of line 2. So we can pull those together and then we can say, okay, so what's d1 dot d2? So that's where you just do minus 2 times minus 2 plus 2 times minus 1 plus 1 times 2. And that's minus 8. Minus 2 is minus 2 if you plot, which gives okay. And the magnitude of d1 is equal to square root of minus 2 squared plus 2 squared plus 1 equals 3. And the magnitude of d2, if you plough through it, comes out it's exactly the same. It's 3 as well. So then you can say that d1 dot d2 equals magnitude of d1 times the magnitude of d2 times the cos of the angle between them. And that's 4 equals 3 times 3 times cos theta. So theta equals cos to the minus 1 of 4 ninths, which is what you're supposed to show. There we go. So basically, you have to take, to find the angle, you have to take whichever form your lines are in, put them in the form so you have the direction vector, and then you can do the dot product thing. When you're trying to find the intersection of the lines, you put them into the parameter form, equate the x coordinates and the y coordinates to find your two parameters, in this case lambda and t, and then check that that's consistent set of equations by substituting into the z coordinates, and once you've done that you can work out the x, y and z coordinates.